Oh, hello there. Welcome back to Math 315. So I'm going to start talking about the last main topic of this class, namely complex variables. Now, some of you may have seen complex variables before. I don't really know. I think there would probably be varying experiences with the people there. So I'm more or less going to start at the beginning, although I'll go fairly rapidly through the elementary stuff. So this first video is just going to be the very basics of complex numbers. And then in the next video, I'll get into some more interesting things involving complex functions. So let's get started. So complex numbers. So, of course, most of you are used to this experience. If you have a quadratic equation, let's say ax squared plus bx plus c, and you want to see where it equals 0, then, of course, you use the quadratic formula, namely this. And then, of course, if b squared minus 4ac is negative, then we say there are no real solutions. And that's where it's generally left in basic beginning algebra classes. But of course, you may have learned in some more advanced algebra class that there are solutions, but you have to expand your universe and be willing to consider numbers beyond the real numbers. So that's where the complex numbers come in. And because the complex numbers, of course, will have a square root of -1. And once there's a square root of -1, then you can take the square root of any negative number. And then this expression will be meaningful regardless of whether b squared minus 4ac is positive, negative, or 0. So that's sort of the motivation. So we could start out by defining. Let's do it this way. I will define a complex number is anything of the form, we usually use z for complex numbers, x plus iy, where x and y are elements of the real numbers. And I, you could think of I as just some symbol, although eventually, of course, we'll find out it's the square root of -1. So we're going to define a set of numbers. It's called the complex numbers. And we'll use this capital script C is the set of all complex numbers. So where x is a real number and y is a real number. Of course, geometrically, you could think of it as just corresponding to a point in the plane, corresponding to the point x, y. So you could, if you wanted to think of it, you could think of it as a vector in the plane, as so, or you could just think of it as a point in the plane, or you could think of it as maybe a sum of these two vectors. This is the vector, well, this is the point x0. So as a complex number, you could think of it as x plus I0, or just x. And then this vector is the vector 0 plus IY, writing as a complex number, or as a vector, it's just the vector 0y. So see, that's the same as this vector. This vector, which you could think of as just IY. Numbers or vectors which lie on the real axis, like this guy, this is called a real number. That's what you're used to. But now, numbers that lie on this axis, of the form IY, are called pure imaginary. The usual terminology is for x plus psi y, then the real part is x. So if we call this z, then this is the real part of z, and then y is the imaginary part. Of z. But now if these are really going to be numbers, I have to tell you how to add them, subtract them, multiply, divide them, and see what kind of properties they have. So we define let's say, addition and subtraction are defined in sort of the obvious way. So if you had c equals x plus iy, and w is, say, a plus ib, then we define z plus w as x plus a plus I y plus b. So all you do is add the real parts and you add the imaginary parts. And of course all this corresponds to, if you think of it as vectors, then it's like saying taking the vector x comma y, and if you want to add the vector a comma b, you just add corresponding coordinates. And this, of course, is the usual vector addition. If you want to do subtraction, then you just subtract these corresponding. Just subtract the corresponding coordinates. So again, that's the usual vector addition and subtraction. So there's nothing new here. At the moment, it's just the usual way of representing a point in the plane as a vector. Nothing that you haven't seen in, say, Calculus 3. But now we want to define multiplication, then it's going to be a little bit different. So if I want to multiply x plus iy times a plus ib, then this is by definition, we want the distributive law to hold, so we just look at all possible products. But when you multiply this times this, you're going to get an I times I. And we're going to make it so that that's -1. So we're going to define this as xa minus yb. That'll be the real part, and the imaginary part will be this term and this term. So xb plus ya. So now I could take that as my definition of how to multiply two of these complex numbers. And when I do this, it's easy to verify that all of the usual laws governing addition and multiplication hold. So in other words, I mean like the commutative law, the associative law, the distributive law, all of those things. It's a very simple check that all those rules still hold. But notice that I times I, or I squared, according to this rule, is just -1. Right? Because if you just had this and this, then the only, so if x and a were 0 and y and b were 1, this would be 0, this would be 0, and this would be -1. So you end up with I squared is -1, as expected. So now we have a set of numbers, namely the complex numbers, that with a notion of how to add, subtract, and multiply, I'll get to dividing in a minute, all the usual laws hold. And you have the special number I, which could be thought of as right here. I is right there. As an ordered pair, it's the ordered pair 0, 1. So as a vector, it's like that. And that has the special property that when you square it, you get -1. All right, well, what about division? I guess if we're going to add, subtract, multiply, we want to be able to divide also. So for division, so I want to know what is 1 over x plus iy. What should that be? Right? If I'm going to be able to divide, I should be able to take the reciprocal of something. And the way to figure out what it should be is say, well, look, I want to try to figure out what complex number this is. So the little trick here is you multiply top and bottom by x minus iy. Of course, we're assuming we don't divide by 0, so let's assume x plus iy is not 0. So if I multiply top and bottom by x minus iy, then the top becomes x minus iy. The bottom, so again, you take all 4 products, each term here times each term here, but of course you're going to get a x, you're going to get a minus ixy, and from these you're going to get a plus ixy, so they cancel, and all you're left with is x squared, and this times this gives you minus I squared y squared, but I squared is -1, so that's just plus y squared. And now that my denominator is a real number, so I could think of it as like this: x over x squared plus y squared minus I times y over x squared plus y squared. So this number here, so now this is a complex number because this is a real number, this is a real number, so this is a complex number, and this is the reciprocal of x plus iy. And once you know how to take a reciprocal, then that tells you how to divide. So if you want to divide, if you want to say divide 2 plus 3i divided by 4 minus 5i, then that's the same as I'll just multiply by 4 plus 5i, top and bottom. So the top becomes, well, I just take all the terms. So I have an 8, and then this is a minus 15. So 8 minus 15 plus I times 2 times 5 and 3 times 4 divided by, and this will be 16 plus 25. So you end up with minus 7 over 41 plus I times 22 over 41. And there's your complex number. So that would be how you divide this number. So now we got adding, subtracting, multiplying, dividing. So we got a real number system here. Of course, sort of the key to what makes all the complex variables work out nicely is to think of the geometry of complex multiplication. So let me take a few minutes describing that. So if you have some random complex number, x plus I, y, you could think of it as this vector. And of course, that vector has a length, which we call r, and it makes an angle from the positive x-axis, theta. These are the usual polar coordinates. So you could describe it this way. And if you look at this triangle, you get the usual polar coordinate formulas, namely x equals r cos theta, y equals r sine theta. So if this were z, I could write z as r cos theta plus I r sine theta. All right, now what if I had two of these numbers and I'm planning on multiplying them? All right, so let's suppose I have two of them. So maybe there's one and there's another. So I'll say, how about z1? And that's, say, r1 cos theta 1 plus I r1 sine of theta 1. So here's theta 1 and r1. And then I have z2 is r2 cos theta 2 plus r2, well, I r2 sine of theta 2. Right, so there's my theta 2, and there's my r2. Then I want to multiply. Well, just write it down. r1 cos theta 1 plus I r1 sine of theta 1, r2 cos theta 2 plus I r2 sine of theta 2. And then when I multiply, let's see, what's the real part is what? This times this. So that's r1 r2 cos theta 1 cos theta 2. And then minus this times this. So you have r1 r2 sine sine. So that's the real part. And then what's the imaginary part? Well, that'll be when you multiply, let's say, these two. So r1, r2 sine cos sine theta 1 cos theta 2. And then r1, r2, I want to multiply these. So it's cos sine, cos theta 1, sine theta 1. Sorry, it's cos theta 1, sine theta 2. So I can write that as r1, r2 times, well, times what? So this first term, when I factor it out, I get cosine, cosine minus sine, sine. And you'll recognize this as the trig identity for the cosine of the sum of these two angles. Plus I, and then again I factor out r1, r2 from here, and I'm left with is sine, cos, cosine. That's the trig identity for the sine of the sum of these angles. So that's what you get. So that's the answer. That's this complex number. So, but see here, it's given to you basically in this polar form. Here, this number represents the length of the complex number, length of z1, z2, and that angle is the angle of z1 times z2. So the upshot is when you multiply two complex numbers, in terms of the polar way of viewing it, what you're doing is multiplying their lengths and adding their angles. Multiply the lengths, add the angles. So if I add these two angles, I might get some angle like that. If I add theta 1 and theta 2, and the length might be something more like that. So here's the length, the product of the lengths, and the angle is the sum of the angles. So that's the geometry. So when you what you do is you multiply lengths and you add angles. Once you understand that, then you can see the geometry of complex multiplication. So for instance, let's look at I squared. Here's I, and here's a right angle. So after all, I you could think of as, in terms of polar coordinates, it's like 1 times the cosine of pi over 2 plus I times the sine of pi over 2. Of course, that's 0 and that's 1, so you just get this equals I. But here it is in terms of its distance from the origin, its length, which is 1, and the angle, which is pi over 2. But according to this description of multiplication, if I multiply I times I, I'm going to multiply the angle. I'm going to multiply the length. Well, that's 1 times 1, so that's still 1. And then the angle I will add, so I'm just going to double that angle. So instead of pi over 2, it's pi. So it's the cosine of pi plus I times the sine of pi. Of course, the cosine of pi is minus 1, and the sine of pi is 0. So you just get negative 1. So when you square it, basically it comes right here to the point minus 1. So that's the geometry behind I squared equals negative 1. All right, so understanding that geometry is crucial. That comes into play constantly. Let me introduce just a little bit of notation that we'll use a lot. So let me notation and a couple definitions, of course. So let's see, if z equals x plus iy, then what looks like the absolute value is z. Sometimes they call it absolute value is z, or a fancier term is the modulus of z, is just the length. It's just the length of it as a vector. So that's x squared plus y squared square root. All right, so it's nothing, you could think of it as r. That's the length of the vector, the modulus of the complex number. And then we also have something that's very useful. If we put a bar over it, what we're going to do is negate the imaginary part. And this is called the complex conjugate. Notice that if you take a complex number and multiply by its complex conjugate, what do you get? So that's x plus iy times x minus iy. That's just x squared plus y squared. That's essentially what we were doing over here when we wanted to understand the reciprocal of a number. You multiply the denominator by its complex conjugate, because that gives you a real number. That's this. So, and of course this is the modulus squared. Sometimes it's often called the norm. So call it the norm or the modulus or the absolute value. It just refers to the length of it viewed as a vector. And we have then that in the complex conjugate. And then of course you could describe some sets. So for instance, so we can use complex numbers. I'll use the abbreviate complex CPLX. Use complex numbers to describe relatively simple regions of the plane. So for instance, if I look at this, I want to look at the set where absolute value z is less than 3, for instance. Then that would just correspond to, well, what if the absolute value of z equals 3? This corresponds to a circle of radius what? 3. So if I want the absolute value to be strictly less than 3, then that would describe that. So here this is distance 3. And sometimes this is called the open disk of radius 3 about the origin, or the origin is just the number 0. It's said to be open because it does not contain the boundary points, namely the circle. If I made this less than or equal, then it would contain the circle, then it would be called the closed disk. So something like this comes up a lot, and also maybe something like this. What if we looked at the set of complex numbers where the real part of z is greater than 1, for instance? Well, the real part of z is just the x-coordinate, so all we're really saying here, if that's 1, all we're really describing is a half plane. All right, so those are the basic notions of complex numbers. And then one final thing what we can do at this point is we can talk about powers and roots. So you want to talk about something like z to the n, or z to the 1 over n. So this would be like square roots, cube roots, and so on. And this would be powers. And to analyze this, it's best to think of the complex number in terms of polar coordinates. So let's do that. I'll tell you what, I'll just pick an example. Okay? So suppose I wanted to take the following complex number and raise it to a power. So I'm going to take one that's going to look familiar. So we'll do something like this. 1/2 plus the square root of 3 over 2i. And I want to raise it to a power. So suppose I want to cube it. Well, let's think of this number in terms of polar coordinates. So, well, let's see. I guess it's really more like here. This is 1/2 and square root of 3 over 2. Of course, I picked obvious numbers here so that it's clear what the angle is. Of course, we know that, that this length is 1, and the angle here is what? It's pi over 3. So I could think of this as the cosine of pi over 3 plus I times the sine of pi over 3 cubed. So I picked an easy case where the radius is 1. But we know from the earlier consideration, if you want to, when you raise things to powers, right, when you multiply complex numbers, then the lengths multiply, the angles add. So if I take a complex number, multiply it sort of by itself 3 times, the length will cube and the angles will triple. Well, the length is 1, so it stays 1, but the angle will triple, so I'm just going to get the cosine of 3 times pi over 3 plus I times the sine of 3 times pi over 3. So that's just cos pi plus I sine pi, which is what? -1. So in fact, when you see, this is length 1, so when you cube it, the length is cubed, but it stays 1, but the angle triples, so now it's going to, if it's pi over 3, now it's going to be pi, and again, I'm coming out here to the number, not I, to -1. So I have that if you cube this, you get a -1. Now, if you want to be my guest, you could actually just multiply this by itself 3 times and take all the products and be careful, and you'll, of course, get the same answer. So in general, how would I take an nth power? Say n is any positive integer. So if n is a positive integer, and if I write z as r cos theta plus I sine theta, then z to the n will be, well, the length will get multiplied n times, so I'll get the length to the power n, and the angle will be multiplied by n. So I get that complex number. All right, so there's a simple formula giving you powers. Okay, but now what about roots? So roots are a little more interesting. So roots. So let's try to calculate some kind of root. Let's say calculate, for instance, what's the cube root of I? How could I find the cube root of I? So in other words, find z so that z cubed equals I. That would be the cube root of I. Okay, so let's write z as r cos theta plus I sine theta. And I have to figure out what's r, what's theta. Well, so what's z cubed? Z cubed is r cubed cos 3 theta plus I sine of 3 theta. And that's supposed to equal I. But then let's write I in terms of its polar form. So that's like 1 times cos pi plus pi over 2 plus I sine of pi over 2. So we want this to equal that. So what we need here is that r cubed is 1. So of course that tells me that r is 1. So the root will again be a complex number of length 1. But the angle, All right, what do I need? I need that the cosine of 3 theta is the cosine of pi over 2, and the sine of 3 theta is the sine of pi over 2. These two together tell me that I need 3 theta to be pi over 2. Well, hold on, that's a little careless. This would be one solution, but there are other solutions, right? Because we know that sine and cosine are periodic with period 2 pi, so it could be that 3 theta is not pi over 2, but it could be pi over 2 plus 2 pi, or pi over 2 plus 4 pi, or pi over 2 plus 6 pi, etc. Or it could be pi over 2 minus 2 pi, pi over 2 minus 4 pi, etc. So it's basically pi over 2 up to multiples of 2 pi. And so now we solve for theta. So theta would be, we just divide by 3. So it's pi over 6. This would be pi over 6. But this one would be what? It'd be pi over 6 plus 2 pi over 3. And this would be pi over 6 plus 4 pi over 3. And then pi over 6 plus 6 pi over 3, etc. And the same for the minus sign, so it could be plus or minus. So what am I doing? Am I getting infinitely many solutions? Well, no. When you look at the solutions, so the basic solution is pi over 6. And all the lengths are 1, so what I'm going to do here is draw the circle of radius 1. And then I'm going to have this where the angle is pi over 6. And then, so that's one solution, would be this complex number. But I could also add 2 pi over 3. If I add 2 pi over 3, where does that get me? Actually, this one I can calculate, right? Because if I add 2 pi over 3, that's 4 pi over 6, so that's 5 pi over 6. And that's right there. That's angle 5 pi over 6. And here, if I add 4 pi over 3, so that is 8 pi over 6. So we get 9 pi over 6. Did I do that right? Yes, 9 pi over 6. And 9 pi over 6 is what? It is, of course, 3 pi over 2. And that's this one. So I start with pi over 6, and then I increase the angle by 2 pi over 3, and then I increase the angle again. So this is 2 pi over 3. And then I increase the angle again by 2 pi over 3. But then if I increase the angle again by 2 pi over 3, I'll get back where I started. So if I do this one, I'm back to pi over 6. So it's really going to be pi over 6 plus 2 pi. But when I take the sine or the cosine, the 2 pi is unimportant. So I'm basically right back where I started. And then if I keep going, I just keep moving around the circle. I get this one, 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 and so on. So I really have 3 roots, and I just visit them over and over and over. So I see that there's 3 roots. So there's 3 solutions. namely, well, so they all have length 1, so that simplifies this problem. So we have the cosine of pi over 6 plus I times the sine of pi over 6. Then I have the cosine of 5 pi over 6, I times the sine of 5 pi over 6, and then 3 pi over 2. So I end up with 3 cube roots of I. If you want to write them out, then of course you just use these values. So this first one would be the square root of 3 over 2 plus I times 1/2. And this next one would be over here. All right, what would it be? It would be minus the square root of 3 over 2 plus I times 1/2. And the last one is this one. Of course, that's just minus I. This one you might have guessed, right? Because let's check. If I minus I cubed, so that's minus I cubed. That's minus I times I squared. That's minus I times -1. So that's plus I. So minus I does have the property that if you cube it, you get plus I. So you might have guessed this root, but these roots would be a little harder to guess. And you see the way it works out, and this is the way it always works out. And anytime you try to find a root, you're going to get, if I was looking for, say, an nth root, I would get n solutions, and they'd be symmetrically located around the circle, where I split the 2 pi of the circle into n pieces. So you're always going to end up with that. So you get 3 roots symmetrically located around the circle. Now in this example, I took I, which had length 1, so the root also had length 1. But if I had taken some other length, then I would end up with solutions which were not length 1, but their length would be the cube root of the length of whatever number I was starting with. So this example basically is a model for looking at any root. So anytime you have some number and you want the nth root, you follow the same procedure. You'll find a few examples of this in the book, so I'll let you take a look at some of those examples. This is, by the way, this is chapter 2 of the text. So what you should probably do at this point is go back to chapter 2 and at least read through there's quite a few sections in there, but they go fast. So read through maybe, at least the first half of the chapter, where the author basically discusses what I've just been discussing. And then what's next will be power series of complex numbers and exponentials, logs, trigonometric functions, and the like. So things start getting a little more interesting when we bring in some infinite series. We get some actually beautiful stuff out of that. But that'll be for the next lecture. So that's enough for today. Again, go into chapter 2 and read through the first 5 or 6 sections at least, and try a few problems. Make sure you can do the problems. Pick problems where there's answers in the back of the book, and make sure that you can get the answers, because this will be important for everything we do. So that's the end of it now, and so I'll leave it there.